Hello, everyone. Welcome back. So last time's lecture was a little shorter because this one is certainly going to be quite a bit longer. Because today we're going to be talking about comparing and contrasting molecules. And this right here is what stereochemistry kind of leads us to. Because we started out having a really good time talking about what different types of stereoisomers are. Now we're getting to the point that we need to actually recognize what these stereoisomers are, and we need to be able to compare them between two different molecules. But the first thing that we need to do before we get to being able to actually compare and contrast is talk about one last type of stereochemistry, which is alkenes, right? Because alkenes are very interesting. Now, notice that whenever we're looking at alkenes, normally we draw them like this. However, there is a second way that we could draw these, right? We could draw them to where both of those methyl groups, because keep in mind these are just CH3s on either side, we could draw it to where both of these methyl groups are actually on this side of the double bond. And as a matter of fact, the interesting thing is these two are stereoisomers. Right? Which seems kind of weird because if we were looking at a different example of something just like butane, right? We could draw butane like this, or we could draw butane like this. But in both of these cases, these are indeed the exact same molecule, right? The only difference here is that it has changed conformation. Right? Remember when we talked about Newton projections, we looked at stuff like this, where essentially this would be like an eclipsed conformer, and then the one on the left here would be more like a gauche conformer. And although these are different rotations around a bond, they are still the same molecule. On the other hand, alkenes are a little different. Because one property of alkenes makes them very different from single bonds, which I said this all the way back in, I think it was lecture two, but we're back to it, where you cannot rotate around double bonds. Right? The rotation around a double bond is much too energetically unstable to actually occur. And so because of that, these two are kind of locked in their position, right? We can say for the molecules here on the right-hand side, these are able to freely rotate, right? So they are freely rotatable versus the molecules on the left-hand side, right? These are locked in their configuration. And because of this, the fact that we're not able to rotate, these are now also stereoisomers. But the question is, how are they stereoisomers? And well, we have to, I guess, talk about this in terms of what each one is showing us. So first, let's redraw out these two alkenes. And we're just going to go through a whole little sort of case study on them. So, first off, there is a way that we label these, right? Because it's not like these are R versus S. Instead, we have new labelings where the one on the left here is what we call E, and the one on the right is what we call Z. Okay? And so, what these tell us is they essentially say where the priority groups sit. Okay? Because the priority groups tell us what the direction of that alkene rotation is. So for an E alkene, the largest groups, right, or the priority groups are opposite of each other, right? Whenever we say opposite, we mean what side of the double bond they are on. Because if we were to draw a nice little dotted line on the plane of where that double bond sits, we would see that there is not shown here, but what we're currently going to show are some hydrogens, right? And so below the plane that we have drawn there Our priority group would be the CH3, right? We would have labeled that as 1. And above the priority group on this side is the CH3, right? Because these hydrogens, which keep in mind whenever we're labeling priority on sides, you can bisect these alkenes this way. Because essentially the left versus the right is what we're comparing between. And then we're talking about top and bottom for whenever we're saying opposite in this case. We can contrast this to the idea of the Z alkene, where if we draw those bisecting planes, we see that both of the priority substituents are on the bottom side of the plane, right? Because the Z alkene essentially says that the largest groups are on the same side as each other. And many people use this very simple way of saying this to remember it, where the Z alkene is indicated by things being on Z same side, also known as the same side, right? So if you ever have trouble remembering it, just use the old Z same side statement to remind you which is the E versus the Z. So these two molecules are vastly different, right? Because essentially, if we're looking down the alkene, we're going to see two different things. So let's say that we were wanting to draw a Newman projection, looking down this E alkene here, straight down that bond right there. What we would see is that the Newman projection for this one, right, we're going to have to use this C right here to show that carbon because it's going to be a little hard to see because these groups are flat, right? This is a trigonal planar sp2 carbon. And since it's trigonal planar, that means that the groups here are all in plane, right? So that hydrogen is right there. So when looking at a Newman projection, we have a group that's pointing straight up and a group that's pointing straight down. That's why I decided to put that carbon in there to make it easier to see. Because the group that's pointing straight up here is the one that's above the eye. It's that hydrogen. And the one that's pointing straight down is this CH3 right here, right? On the opposite end, we have the back carbon, where pointing straight down is a hydrogen, pointing straight up is a CH3, right? We can see just by taking a look at this simple Newman projection that there is going to be some eclipsing interactions, right? We have both the hydrogen and the methyl on the bottom, the hydrogen and the methyl on the top, right? So these are all just classic eclipsing interactions. But compare this idea to what happens if we look at the Z isomer, right? Because this Newman projection is going to look just a little bit different. So on this one, if we're looking down this bond where the I is here, we see that both the hydrogens are pointed upward and both of the methyl groups are pointed downward. And so now we have, and I'm going to draw it in red because it's so much worse, a big eclipsing interaction because this is not only a normal eclipsing, but it's also two sterically bulky groups, right? So when we think of these in terms of stability, they are also different for stability, right? Large groups cause more strain. So what we're saying is that the Newman projection here on the left-hand side is essentially more stable, right? Because there is less strain than here on the right-hand side, which is less stable because it has more strain. Okay? So what this looks like in terms of energy is that essentially the lower energy form, the one with less strain, is always E, and then the one with the higher energy and higher strain is Z. Okay? So whenever we're looking at these, they have differences in energy. So we have to ask ourselves the question, right? How are these stereoisomers? Well, they follow the normal definition of stereoisomers to where they have the same molecular formula, they have the same connectivity. It's just things are differing in physical space. But the question is, which type of stereoisomers are these? Because we have two choices, right? We have enantiomers, which we've already discussed multiple times in the last couple of lectures, where they have the same physical properties, right? Or they are diastereomers, and they have different physical properties. And if you think about these terms, normally when we're thinking about enantiomers, we're thinking about all the stereocenters change. But technically, even though the alkene is a stereocenter, right? So keep in mind that we do still call this a stereocenter. So it does come into play when we're looking at the idea of calculating stereoisomers. But the thing is, even though that stereocenter changes, there's one thing that does actually change with it, which is energy, right? And energy is a physical property. Since energy is a physical property, that tells us that these have to be diastereomers. Okay? So the big conclusion to this idea is that E and Z isomers are always diastereomers. And I want to make it clear that they are always diastereomers, even if there are other stereocenters in the molecule. So if all the stereocenters change and then the alkene changes from E to Z, it is automatically a diastereomer. None of those other stereocenters actually matter. Okay? So, with that being said, we have to have some rules for identifying E versus Z, right? Because it's just like when we're looking at R, R, and S, because it is this idea where it's just a new stereo center that we're looking at. And so essentially what we're going to see is that these have the same rules as R and S for priority, but now we only care about priority one off each side of the alkene. Okay? So let's take a look at a couple molecules so that we can kind of identify E versus Z, and then we can kind of wrap that up and move on to the more fun stuff. So let's say we had a molecule that looks like this. Okay, so if we wanted to say whether or not this is E or Z, the first thing we want to do is we want to cut the alkene right down the middle here. Because the left versus the right side are the ones that we're looking for who has the highest priority on each. So on the left side, we're comparing a hydrogen and a CH3, right? Remember for R and S priority, you start from the carbon of interest, which the carbon of the alkene is our stereocenter, and then you move out one atom at a time and you check and see which has higher priority. So we run into the H, we run into the C. Carbon has a higher atomic number than hydrogen, therefore it takes number one. Looking on the right side of the alkene, moving out from this carbon, we hit a fluorine, we hit an oxygen. Fluorine has a higher atomic number, so it's going to take our number one. So, where are these groups in comparison to one another? Now we're looking down the alkene by this red bisector, and we see that they are on opposite sides, right? The CH3 is below, the F is above, so that tells us that the priority groups are opposite. And if the priority groups are opposite, that is an E alkene, right? Because remember, if they were on the same side, it would be a Z alkene. So let's take a look at another example. Okay, so for this one, we're looking at a bit bigger of an alkene, right? A bit bigger of a molecule. So first thing we're going to do is we're going to bisect this alkene and we're going to take a look at both sides. So starting with the left-hand side, if we move out one atom, we hit a CH3 and or a carbon and a carbon, right? For R and S priority, we say if you hit two things that are of the same atomic number, you have to then move out an additional atom. On the top one, we hit three hydrogens. On the bottom one, we hit two hydrogens and another carbon. So that bottom one takes our priority number. On the other side, starting from here, we move out a single atom. We see a carbon, we see a bromine. Bromine has a higher atomic number. It's going to be our number one. So then, looking at the red line to bisect our alkene, we see, okay, both ones are below the red line. That says our priority groups are on the same side, right? So if they're on the same side, that tells us it is a Z alkene. All right. Last but not least, let's do one more of these. Okay. So for this one, if we were to bisect our alkene, we see that on the left-hand side, we move out one atom, we hit two carbons. So we have to move out another atom. We hit two hydrogens and two carbon, or in a carbon on each of them. You'll notice here that these two groups, right, which I'm circling now, they're both the same group, right? And since these are the same group, essentially what we're seeing here is that this is achiral, right? So essentially alkenes can also be achiral, and therefore we can't label them as E or Z. So just like we see normal achiral carbons, essentially these alkenes share the same rules where you can't really give one an absolute configuration because remember E and Z is essentially the absolute configuration of an alkene because it's just not chiral and therefore you can't label it. There's one other thing that comes with these alkenes that I'm sure everyone's very excited for. That is a new nomenclature rule. Just like with RNS, that absolute configuration, we now have to include E and Z in our nomenclature. So I'm sure you're starting to recognize that the more things that we add onto nomenclature, the more difficult it's going to get. So hopefully you were able to memorize most of that chart going into exam one because it's going to come back with a little more on top of it because now you'll have to do R and S and now you'll have to do E and Z. So essentially the way E and Z works is if a chiral alkene is present, you must indicate E or Z in parentheses before the prefixes. All right. And one last thing is it comes after R and S stereochemistry. Okay. So let's see this rule in action. Let's say we were given a molecule that looks like this. All right. For this one, we have both stereochemistry and we have an alkene. So we need to figure out exactly what's going on here. Still, the rules follow where we have to figure out first what is the longest chain. And so looking at this, it's pretty simple. I made it easy enough that you can see the longest carbon chain right down the middle here. 1, 2, 3, 4, 5. And the reason I labeled it this way is because the first thing that I saw was this alcohol, which we know is our priority group. And since it's our priority group, it's going to take the suffix of all. Okay, for other things now, we have stereochemistry on that alcohol. So let's figure out what that is first. So looking at this, if you were to do your 1, 2, and 3, you would find it's a counterclockwise rotation, which is S. For the alkene, in this case, we have some hydrogens that aren't shown, but I'll draw them in green. Right? If you were to bisect this and look at it, you would see that the largest groups are on opposite sides. So this alkene is E. So what this is going to look like is in our actual name for this molecule, we're going to have first, because the E or Z comes after R and S stereochemistry, we're first going to list the stereochemistry of the alcohol, right? It is on carbon 2 and it is S. Okay? Next up, we're going to have our alkene stereochemistry, right? Because it's a chiral alkene. It starts on carbon 3, and it is an E alkene, so it's 3E. Then we have prefixes. In this case, there are no side chains or additional functionality, so we don't have any of that. We have our longest carbon chain, which is 5, so that's pent. The alkene starts on 3, right? Because our infix is En. And last but not least, the alcohol is on carbon 2, so it's 2-all. So overall, this IUPAC name is 2S, 3E, pent, 3N, 2-all. Okay, so with that being said, there's more of these that are practice problems in your practice worksheet for this week. I suggest to try those out if you need some more time to try nomenclature. Now let's get to the fun stuff, right? Now that we finally finished up the idea of stereochemistry, we are now going to move on to relating molecules. And so you've already done a little bit of this in the previous week's assignment, but this time we're going to extend it a little further because what we're essentially asking is you're going to have two molecules and you're going to have to ask yourself, how are these two molecules related? Right? So let's say you're given these two molecules as an example. So how are these related? Well, so far throughout the course, we have talked about a lot of different options, right? These could be the same molecule, right? It could just be a couple rotations in order to look like they're the exact same. You can also call this identical, right? Because they are completely matching. They could be completely different molecules, right? Meaning they have no relationship. Those are the very simple ones, right? Just they're either the exact same or entirely different. Another one is, remember earlier in the semester, we talked about things that have the same molecular formula but different connectivity. Those were constitutional isomers. Hopefully you didn't forget that those were around, right? Because those do exist here. Another one that we've been talking about this week specifically is enantiomers. Right? They could just be mirror images of one another, non-superimposable mirror images of one another. Another type could be diastereomers, right? Because they could just be where some stereocenters have changed, but not all of them. Another thing they could be, because don't forget, we have some other things that we've talked about. We've talked about conformational isomers, or as we have called them in the past, conformers. Right? These are like rotations around single bonds that just alter which group is pointed in which direction. Right? That's when we went through Newman projections and chair flips. Those were all conformational isomers. Another type that we haven't talked about yet, but exists, is rotamers, right? Rotational isomers. All of these could be what we would say is the relationship between the molecules up here. Now, that being said, these bottom two, labeled as F and G, conformational isomers and rotamers, don't worry about them, right? This is not important for quizzes or exams. But all the others, they're going to be pretty fair game. So the question we have to ask ourselves is how do we know which one it is? How do we know which to choose? And that is where we come to a very, very handy flowchart for our relationships, right? Because all of these terms up here are related to one another in different ways. Okay, so anytime you see this question about how are these molecules related, I want you to start by looking at them and going through this flowchart one at a time because it's going to help you differentiate this without confusing yourself. The first thing I want you to say is, okay, looking at these two structures, what is the molecular formula? Right? Which seems really silly because the molecular formula is kind of one of the simplest things to look at. But that's why we're starting here, is because it's very simple. Because you can split this into two different directions, right? You can either have the same molecular formula or you can have a different molecular formula. And funny enough, this split automatically tells us something about the molecules. That is, if they have a different molecular formula, they are different molecules, right? They can have no relationship if the molecular formula is completely different. Versus if they're the same, they can have multiple types of relationships, right? And the first relationship we can ask about is what about the connectivity? Right? Because the connectivity is telling us how are the bonds connected to one another. Well, we can say that there are, once again, two split paths that we can take from here. We can have either the connectivity is the exact same or the connectivity is different. And if you go down this little path of different connectivity, it actually is just the definition of something else. Same molecular formula, different connectivity is the exact molecular formula for constitutional isomers. All right? But if we go down the path of the same connectivity, we've run into a new question, which is, okay, if they have the same molecular formula and the same connectivity, the only thing that can actually be different about them now is their stereocenters. All right? And the stereocenters now have three different splits that they can go down. The first two are the same as the ones we've been seeing before. The third one's a little different. So for the split to the left, we're going to keep it similar to our previous splits, where it's all of them are different, right? If the stereocenters have all been changed, that's the definition we used previously for enantiomers, right? We said that they are non-superimposable mirror images, but they are also where all of the stereocenters have swapped. They are now all different. Versus if all the stereocenters are the same, funny enough, same formula, same conductivity, same stereochemistry, you're looking at the exact same molecule, right? Those things are identical to one another. The last split, as you may expect, is that not all of the stereocenters have to be the same and not all of them have to be different. You could have the choice where some, but not all, are different or changed, right? And that was the definition we had given previously for diastereomers. And the reason I give you this flowchart, the reason it's important, is because if at any time in the previous steps something is different before you even reach stereocenters, the stereochemistry doesn't even matter. Okay, we're going to see some like that a little later, but let's return to this idea of what we had presented to us up here. How are these two molecules related? Well, let's draw them out down here, right? Because this is going to be where we actually figure out how these two things are related. Whoops, not Br, it should be an OH. Okay, so first thing we need to do is we need to figure out the molecular formula, right? That's the top of our flowchart. That's the first thing we need to do. Are they the same or are they different? So let's figure that out. If we look at the molecule on the left, its formula is C6H11O Br. Okay. If we look at the molecule on the right, it is C6H11O Br. So these have the same molecular formula, right? So we're going to the right of that molecular formula. We have to ask another question. Connectivity. Are these connected the same? So the question may be, how do you figure out whether or not something is connected the same? Well, the best way to do it is by taking what you have on one side and numbering it to where you see what's connected to each carbon, right? In the case of what we see over here, on the left-hand side, if we were to say put bromine on carbon 1 and we number around, we would put the oxygen on carbon 3. And keep in mind these numbers are just arbitrary. They don't have anything to do with something like nomenclature, where we would have put the number 1 on the oxygen. I'm just deciding to number these in an arbitrary way because all we want to do is we want to check and see if the numbers match between the two of these here, right? So the bromine was on 1, the oxygen was on 3. Can we do the same numbering on the compound on the right? Well, looking at it, we can put the 1 on bromine. That's easy enough. If we number this way, there we go. We can put the 3 on oxygen. There's the 4, the 5, and the 6. So connectivity-wise, these are the same. They have the same things hanging off of each carbon that we have numbered. That means we've gone down that right branch again and we've hit stereocenters. So the question is, are they all the same? Have some but not all changed, or are all of them different? We can do this one of two ways, right? And I'll show both of them as we go throughout this lecture. The first one is we can take one of these guys and we can rotate it in order to figure out if it matches the wedges and dashes. Now, that's not always going to be useful. You may find it more useful to do the absolute configuration. That's why we're going to do both of them. First, I'm going to show you the rotation, though. For the rotation, let's say we rotated around this axis here on this first molecule, and we just flipped it over, right? What that'll do is it'll give us a rotation in which we've now flipped it to where that top side is now on the bottom. And by flipping it 180 degrees, the bromine that was pointing back into the page now rotates 100 degrees, 80 degrees, and is pointing towards the front. And the OH that was pointing towards the front is now rotated, and it is now on the dash pointing towards the back. Now, looking at this, it's pretty obvious, right? Because now the bromine and the OH are in the same spot, and we can see just by a visual comparison that we have both the bromines on wedges, but then both the oxygens are different. So in this case, I would say that some, but not all of the stereocenters are different, which means that these are diastereomers, right? Keep in mind this isn't the only way we could have done this. We could have done it by labeling the absolute stereochemistry. If you were to do that, you'd find that in the first structure, the bromine is S and the alcohol is S, right? And then in the final structure, you'd find the bromine is still S, right? It did not change, but then the alcohol was R. And since between the two, the alcohol went from S to R, that means some but not all changed. And so you still end up with the idea that these are diastereomers. Okay? But keep in mind the way that we went through this problem, right? The first thing we did was we checked the formula. The second thing we did was we checked that connectivity. And then after those were all the same, we moved on to stereocenters. Okay? So that being said, this is my PSA that these should be the last thing you worry about. All right? Now, with that being said, we're going to go through a lot more comparisons, okay? Because I can tell you right away, this will be on your exam. This exact concept will be on your exam. And it will be presented in the exact same way as it is here, the exact same way on your homework assignment, and the exact same way in the practice problems. Okay, so let's hop on and let's do quite a few comparisons to figure out exactly how to do this in an efficient manner. So let's do a second example. So for this one, we have these two structures here. All right, let's figure out what the relationship between these two molecules is. So first thing we got to do, we always, always, always have to start by figuring out that molecular formula. Now, you could have a pretty good eye for the molecular formula, and you could also just have to sit there and count it. I would hope that as you go through this, you start to get a good idea of whether or not the molecular formula is correct. I will say that if you have the same number of carbons and other atoms, as long as there's no difference between double bonds, they're going to be the exact same. So the first thing I'm going to do is I'm just going to count up and I'm going to find out how many carbons and other atoms there are on here. And so I see on the structure on the right, there's 6 carbons. So that's C6. And there's a chlorine, right? I'm not counting the hydrogens because there's no double bonds. Oh, whoops. And then on the compound on the right, I see there's 6, and a chlorine. So that tells me that since there's no double bonds in any of these, they're the same molecular formula. Okay? So same molecular formula means that now we have to check our connectivity. So looking at the structure on the right, again, best way to do this is to label the carbons. So there's 1, 2, 3, 4, 5, and then we'll even label that one 6, because again, this isn't nomenclature labeling, it's just labeling to make sure we know what's going on. This one over here is a little interesting, whereas 1, 2, 3, 4, 5, 6. So for this one, we see that, okay, we have attached to carbon 3 in both examples is carbon 6, but then attached to carbon 4 in one example is just two hydrogens. Attached to carbon 4 over here is a chlorine. Attached to carbon 6 over here is a chlorine, but over here is just two hydrogens. You may be able to tell these are different connectivities, right? Not all of the same stuff is connected to the same carbons in both cases. So this is the same molecular formula, but different connectivity, right? The good news is I don't care about any of the stereochemistry because we never got there on the flowchart. Because if we take a look at that flowchart once again, same molecular formula, different connectivity is immediately constitutional isomers. All right. So these, in fact, are constitutional isomers. Okay. And the way you can often identify these is due to these chain lengths and the difference in where functional groups are connected. Right? It's very nice when you don't have to worry about labeling these as R or S because you stop before you get to that stereochemistry part as well. Okay, let's move on to another example. All right, this will be example number 3. So for this one, let's say that we're comparing this molecule here on the left versus the molecule over here on the right. Okay, step 1 is to check the molecular formulas. Now, you may find that in this case, they do have the same molecular formula, right? I'm not going to write it entirely out because we're going to be writing a bunch of different stuff on this one. They have the same molecular formula. Now, let's take a look at connectivity. So, on the molecule on the left, we're just going to label this one relatively arbitrarily, 1 through 5. On the molecule on the right, we got to make sure the bromine's off carbon 2 and the alcohol's off carbon 3. Looking at this, we see that if we number it in this direction, that is true. So in this case, we have so far same molecular formula, same connectivity, right? Everything that's connected in one is connected the same in the other, which means now we're down to our stereochemistry, right? And remember, we can do this one of two ways. We can either rotate it or we can figure out absolute stereochemistry. We're going to do the absolute first this time since we did the rotations first last time. Then we'll do the rotations afterwards in just a second. So looking at this one, on the structure on the left-hand side, where the bromine is, if we wanted to do R or S, we'd see 1 for the bromine, 2 for the chain with the oxygen, 3 for the CH3, and the hydrogen's already in the back. That is a clockwise rotation. That is R. For the alcohol, it is just using either rotations or you can do the right hand rule. You'll find that it is S. On the right hand side, we have the OH in this case is R, and where the Br is S. So in this case, looking at it, the bromine starts out R and it changes to S. So this is now different. And then the alcohol carbon starts out S and ends up R. So this is also different. Since all of the stereocenters in this case changed, right, there's none that we've labeled as the same, these are enantiomers. Okay? But what we're going to do is we're now going to check that by doing some rotations. Because remember, we can rotate these to try and get them into the same orientation so that we do direct comparisons between the bonds. So if we wanted to do a rotation of this one, first thing we're going to want to do is we can actually rotate along this, I'll draw it in pink, vertical axis here, right? We can do a flip because what that'll do is it'll put the bromine on the right hand or on the left hand side of the molecule. And since it's a 180-degree flip, it's going to change that stereochemistry. Same with the alcohol here. We can do another flip right across this. We'll draw it in green axis here. Right, we can do a flip, which is going to put that bromine in the same position as it was in our original molecule. But keep in mind, by doing this flip, it changes that wedge to a dash. And then same thing with the alcohol, changes its dash to a wedge. And looking at this, we can see pretty easily that the bromine in the second molecule is different because it was on a wedge and now it's on a dash. And the alcohol is also different because it was on a dash and now it's on a wedge. So these are very clearly enantiomers, right? Because all of the stereochemistry is changing. Okay, let's do another one. So for this one, we are going to have the structure right here versus this structure right here. Okay, so looking at these, they look pretty similar, right? But if you were to start out and say, all right, let's figure out the molecular formula, what you'd see is that in the first structure, it has 7 carbons, but in the second structure, it only has 6. All right? Because of that, these have different molecular formulas. And anytime we have different molecular formulas, it's very simple and easy. These are just different molecules, right? They have no relationship whatsoever. So again, it's very helpful if you use the flowchart and you start from the top because essentially if you run into the situation, you don't have to worry about anything else in the molecule and it's very quick and easy just to say they are different. All right, let's move on to another one. Okay, for this one, we have this molecule here, and then we have another one on the side. Okay, so for this one, step one, molecular formula. Looking at it, we see there's one, two, three, four, five, six, seven carbons on the one on the left. There's one, two, three, four, five, six, seven carbons on the one on the right. Bromine on each. There's no double bonds different. So that tells us that they are the same molecular formula. All right, connectivity wise, the structure here on the right or on the left, one, two, three, four, five, six, and that'll be carbon seven. Looking at the one on the right, we can get it numbered the same if we just start from the right-hand side. Five, six, and seven. So these also have the same connectivity. Okay. So same molecular formula, same connectivity. Now it's just a question of our stereocenters. So this time we're going to do rotations first, right? Looking at this, we can take this structure right here and we can flip it across this plane here. We do that flip, we essentially end up in this position here, where now our bromine is facing down that way on a wedge. That methyl is also on a wedge. And then we can do the same thing where we flip it across this axis here to put everything into the same spot as what it is in our starting structure. And what we see is now this methyl group is on a dash and this bromine is on a dash. So, what this would lead you to believe is, okay, looking at this, the bromines have the same, but the methyl groups are swapped. These must be diastereomers, right? But that's where this is a little tricky, right? The reason that it's good to be able to label things as R and S is because if you took the time to think about that methyl group and whether or not it's R or S, you'll find this is achiral, right? Because the two CH3s are connected to the same carbon, therefore it doesn't have any chirality. So it actually doesn't matter whether or not it's dashed or wedged, because it's the same either way. That tells us that the only thing that actually matters is our bromine. And the fact that these are the same tells us that these molecules must be the same molecule. Right? To prove this further, looking at our R and S, we see that if we were to do it for the bromine in the first example, it is S. If we do it for the bromine on the right, it is S, but we can't do it for either of the achiral methyls, right? Because achiral can't be R or S. So anytime you see something achiral, it doesn't even come into, I guess, account whenever you're trying to figure out if the stereocenters have changed or not. So since those are all the same, it's just the same molecule. All right, let's do another one. All right, for this one, we're gonna get a little bit tricky. So let's say we have something right like this versus something like this, and we are saying to figure out the relationship here. Well, looking at these, we can ask what's the molecular formula in both. We see one, two, three, four, five, six, seven, eight carbons in the first example. There are eight in the second one as well. There's a bromine and oxygen. These have the same molecular formula. And now you may be tempted to immediately say, oh, it is super obvious that these do not have the same connectivity. But don't be so hasty to say so, because if we number these, right, looking at the one on the left, if we start by numbering that carbon right there, we call that 8. We can do the same thing on the molecule on the right, and we see 1, 2, 3, 4, 5, 6, 7, and 8. Off of carbon 3 is carbon 8, carbon 2, and carbon 4. Great. Off carbon 4 is the OH, and off of carbon 5 is the bromine. These actually have the same connectivity. That means the thing that might be different is their stereocenters. All right. And this is where I've highly recommend taking a moment to just think about whether or not you want to do rotations in your mind or if you want to do R and S labeling, right? Because a large number of rotations can be very confusing, but you can use absolute stereochemistry to make it really, really simple for you, right? Take, for example, looking at this molecule here on the right or on the left. So carbon number 3, this carbon right here, if we were to label this as R or S, we would find that this is actually R, right? The one with the alcohol off of it is also R, and then the one with the bromine is S. On the right-hand side, we have this molecule where the methyl is R, where the alcohol is also R, where the bromine is it's S. So in both of these cases, these two are the same, right? The ones with the alcohol are also the same, and the ones where the bromine is are the same. So these are actually the same molecule. And this is much, much easier than doing all of those rotations, right? Because if you were to sit there and do all of those rotations, you could end up rotating something incorrectly, and then you may think that they're diastereomers because you accidentally flipped a wedge or a dash when you didn't want to. But if you label as RNS, you'll actually never be wrong. Okay? So I highly recommend doing RNS. I'm not even going to show the rotations for this one because it is only 2 rotations, but they can get a little confusing. Okay, let's do another one. All right, for this one, what if you were given a couple of chairs? So, as a reminder, in this course, everything is fair game since the beginning of the course. So, because everything is fair game, same is true about chairs, right? Chairs are fair game because we've already looked at them once before. Okay, great. So, let's take a look at these two chairs and let's figure out what the relationship between them is. So, looking at both of them, I'm hoping it's very obvious they have the same molecular formula, right? They already look incredibly similar. Let's take a look at the connectivity. So let's say we were to label the one with the alcohol as 1, and we just go around clockwise, 2, 3, 4, 5, and 6. We see that the bromine's off carbon 3, the chlorine's off carbon 5. Can we number the other one in the same way? Yep, there's 1, 2, 3, 4, 5, and 6, where the bromine's off carbon 3, chlorine's off carbon 5. So looking at this, that is same molecular formula, same connectivity. And just from first glance, I see the OH and the bromine are up in both and the chlorine's down. Therefore, these must be the same, right? That's not exactly the case, though. Okay, let's take a look at these in their bond line form. Okay, so let's convert to bond line. Because if we take a look at these in bond line, they may tell a little bit different of a story. All right, so in the case of this one over here, we do have the OH pointed up, we have the bromine pointed up, and we have the chlorine pointed down. This one on the right, we have the OH pointed up, the bromine pointed up, and the Cl pointed down. Now it may become a little bit more obvious looking at this, right? Because we can't just compare these two directly one to one because they're in different orientations, right? If we wanted to actually compare these, we could do a little something where we flip this one across that axis, right? And that rotation that flip will essentially put it into the same orientation as the um, original starting molecule, the one on the left. And we see in this case that these stereocenters have all changed, right? As a matter of fact, these are enantiomers, right? Because the wedge for the OH became a dash, the dash for the Cl became a wedge, and the dash for the bromine, or the, sorry, wedge for the bromine became a dash. You could have also figured this out by doing RNS labeling for the stereocenters, right? You would find that for the chlorine on this side, it was R, the OH was R, the bromine R, and on the other side, the bromine was S, the OH was S, and the chlorine was S. But when you're looking at these chair conformers, I highly, highly recommend take them into bond line, right? Because there's no way that you're going to be able to tell whether or not these are actually the same molecule or different unless you take them into their bond line conformations. All right. That being said, we still have more examples to go through. Let's keep it going. Let's look at example 8. So for this one, we're bringing in an alkene, right? Let's say that we did this here. So looking at these, it should be pretty obvious that these have the same molecular formula and they have the same connectivity. But between the two, we see that, okay, in one case, the bromine, right, it is R. In the other case, it is S, so that one is changed. In one case, the alkene is E. In the other case, it is Z. All right? So in this case, every stereocenter has changed. Okay? But these are diastereomers. Okay? And the reason for this is because the stereocenter for the bromine doesn't even matter, right? All alkenes will make diastereomers if they change. All right? That is the exception to the rule. Alkenes always make diastereomers. So check and see if those are different because they will make diastereomers. Now, that is, of course, if the things have the same molecular formula and same connectivity. All right, let's do another one. For this one, we're going to start off with a nice, simple Newman projection. Because again, everything is on the table. All right, so we'll do that versus this structure here, which is just in bond line. So the first thing you're going to want to do here is it's about impossible to figure out if these are the same or different, just given one of them's in a Newton projection. You could if you were very, very good at looking at Newton projections, converting them in your head very quickly. But the first thing that we're going to do here is we are going to convert to bond line. Everything is easier when you convert into bond line. And if we do that, what we'll find is, all right, we have our ethyl and our methyl there, and then the OH is on a wedge. The Br is on a wedge. So great. Looking at these two, we can say that they have the same molecular formula, right? The one on the left and the one on the right, they look pretty dang similar. But if we take a look at these in terms of their connectivity, and we start over here, 1, 2, 3, 4, and 5, there's no way on the other one that we can put the alcohol on carbon 2 and the bromine on carbon 3 while having everything connected the same. Right? The bromine will end up on carbon 2, the alcohol will end up on carbon 3. So these have different connectivities, therefore they are constitutional isomers. Okay. We have done a lot of comparisons. If you want to try and do 30 more of them on your practice worksheet this week, there are 30 more of these comparing and contrasting molecules. All right. I highly recommend doing them. They'll help you a lot in terms of figuring out your exams and quizzes. But with that being said, we're going to close out the stereochemistry chapter with one last little piece of lecture, which will not be found on any quizzes or exams, but it's going to be incredibly useful for biochemistry. All right. So if you're going to go into biochemistry, pay close attention because these things will show up in your biochem class. And these are called Fisher projections, right? So as a just quick note, these will not be on your quizzes or exams unless for extra credit, all right? Because that is always an important thing to disclose. So yeah, these are useful for carbohydrates and sometimes in biochemistry for things like peptides. All right, so we'll just put that as the quote here, useful for carbohydrates and biochemistry. But for this course, I'm not going to make it too big of a deal because you're going to go over it more in that course. Essentially, what these things are is they kind of look a little something like this. All right, where it looks like a spine, right? And on either side of the spine, it splits between a couple of different atoms. So, what this is actually showing is essentially it's saying that the things on the actual spine itself, right, going up and down, those are coming in and out of the page. All right, versus the things on the, or sorry, they are going sort of into the page, versus the things on the outside are kind of coming out towards you, right? So if we were to show this with a little bit of actually stereochemistry, and I'm only going to do it for the top piece here, essentially it kind of would look like this here. I'll just make this CH3 and this the OH. Okay? And this is a very confusing way to look at it. A better way to think about it, in my opinion, is think about it in terms of the bond line structure. What the bond line structure is kind of showing for these Fisher projections is it's as though we're looking from above the bond line structure down towards it. All right, but the bond line structure does not look the same way that you would expect it to. It actually looks a little bit like this. So rather than being in the normal zigzag conformation, instead, this one is looking in sort of this like curled in direction. Okay. And we are looking at it from above. So it's like we have an eye that's sitting up here and looking down. And so essentially what that eye is seeing is off in one direction, it sees this carbonyl with the hydrogen attached to it. And then coming out of the page is what's on the left side, right? So that is what is on our wedges, quote unquote. And then on the other side is what is essentially on our dashes, quote unquote. But the thing is, with all the bonds being rotated like this, they don't look normal, and that's why I don't want us to focus on them for this class specifically. Because they're not in this normal zigzag conformation, but they're all facing the same direction. Right? So for Fisher projections, bonds have to be rotated, we'll call it inward, right? Because they all kind of point towards this little ring here. If we were to take these bonds and rotate them out, right? So we can rotate quote unquote out. What we would be doing is we would be taking all of these bonds and we would slowly be rotating them to where they're in the normal zigzag conformation. So this bond would have to get rotated in order to twist this alcohol down this way, twist this chain up this way, and then you'd have to do the same rotation for every other piece of this chain. And what you would end up doing is you'd end up getting our classical zigzag conformation, but you'll notice now it looks very different, right? Because now it's got, this is still on the dash, but now this is on a dash, this is on a wedge, and this goes right here. Right, so you're essentially doing these rotations to curve it in and the rotations to put it out so that the Fisher projection is showing that view from above, but it is the Fisher projection for this final structure that we have drawn right here. Okay? We can do Fisher projections by making them, just doing things in the opposite order. Okay, so let's say that we were given a bond line structure that looks a little bit like this. And we wanted to make it into a Fisher projection. How do we do that? Well, what we have to do is we kind of have to get it into that conformation that we were looking at beforehand, right? Where all the bonds are sort of rotated inward. So how are we going to do that? Well, first is we're going to have to flip this thing, right? Because notice how if we want all these bonds to rotate inward, we kind of have to have something pointing on what looks kind of like a mountain peak. So we can flip it first, right? Across this blue piece here. What that'll do is that'll get us to the point where now this carbon is ready for the rotations to occur. All right, but keep in mind that flipping has already swapped out some of our stereochemistries. Okay, now we're going to do that rotate inward. All right, so all the bonds are kind of getting rotated to where now they all are facing in towards one another. So the first one isn't going to change, right? The stereochemistry there is the exact same. But now the second bond has been rotated around to where now the oxygen is pointing out this way, and it's moved from being back in the paper to coming out towards us. The chlorine got rotated twice, right? First one was it got rotated downward and then it got rotated inward. And since it went through two full rotations, it changed its stereochemistry to a dash and then back to a wedge. Now, I highly recommend use a model kit to understand this part because it's hard to show on paper, and I don't want to draw out all of these rotations considering it won't be on your quizzes or your exams. It's just a useful piece to know for biochem in the future. Last little thing is looking from above here. If we were to look down onto these bonds, this would give us the Fisher projection. So up at the top is going to be that NH2, right? Because it's in plane. And now, just like before, we said that our wedges are going to be on the left-hand side. So this is where our CH3 is. We also have our OH, our Cl. On all of the dashes, on the first one, we have an OH, then we have an H, an H, and then we can't forget that CH3 that's in plane on the bottom. That is the Fisher projection for this molecule. So again, you will not see this on your quizzes or exams. It's just something useful to know for biochem. So if you're going into biochem, take some time to look at the book for this section. It shows all of the rotations. It may make it a little easier to see. But with that being said, that closes out stereochemistry for us. Next time, we will be looking at our first set of reaction chemistry. So with that being said, I'll see you next time for that piece of lecture.